Hi everyone. Let me check my audio levels. Looks good. Okay. So um, uh, so today I don't know if we'll need the whole class, but today I wanted to do two more problems in solving problems with Newton's laws, and this should cover everything that you really need to know for the assignment. Well, I wouldn't say cover. I mean, all the material is in the pre-recorded lectures, but we will have practiced then everything that we've done that you will need to do for the assignment. Okay, so last class, what I did was I did an example of just an inclined plane in a single box. Okay, and there was a bit involved because you had to calculate the various components of gravity, but it gets more complicated when you have two boxes. Okay, and or more, but we've only done two boxes in this course. You've got two boxes and they're interacting with one another in some way. Um, in this particular case, they're attached by a string, and you ask for the acceleration of the system. Okay, so we're going to do that today. Okay, we're going to look at two examples where we have two boxes interacting with one another. All right, so this is question number two because question number one was the one I did on Tuesday. So question number two here is a 13 kilogram box on a flat table with a coefficient of kinetic friction of 0.25 is attached by a string to a 6 kilogram box dangling off of the end. Okay, and I want to know the acceleration of the system. All right, so as usual, we start off by drawing a diagram. So over here, let's start with a diagram. And we have a flat table this time. So here's my flat table, like that. And we have two boxes. One box is on the top of the table like this. And this one is 13 kilograms. We'll write that up here. Okay. And we have another one, which is dangling off of the end here like this. And it is 6 kilograms, like that. And the two are attached to one another by a string. So here's this string here, and it goes like that, and then it comes straight down like that. And of course, to keep the string in place, there's a pulley like that. Okay, so if you reread the problem, you see that the 13 kilogram box on a flat table with a coefficient of friction 0.25. You really can't draw the coefficient of friction, but it's right in here. I guess I could just temporarily draw it in there. Okay, there's friction in there. Um, that 13 kilogram box is attached by a string to a 6 kilogram box dangling off of the end. Okay, and we want the acceleration of the whole system. All right, so what you see there in black is what you would physically see if you walked into a lab. And now what we do is we start to assign forces to each of the boxes and then solve the problem. Okay, now you've got two boxes, and so what you need to do is you need to look at each box separately. So we're going to do the free body diagram for that one first, and then the free body diagram for that one second. All right, and you need to do each one separately because otherwise you'll get confused between which forces are acting on what. Okay, so you've got two bodies, 13 kilogram and 6 kilogram, and we'll look at the forces on each one of them. Okay, so let's start with the 13 kilogram first, and it has gravity acting on it. Okay, so we're going to attach all of our forces to the middle here like that, and so here is the force of gravity. It's straight down, and unlike the problem where the box is on an inclined plane, here you don't have to worry about resolving the vector into its parallel and perpendicular component. Okay, it's straight down, and that's good enough. Okay, we don't have to. There is no parallel component there. All right. So let me see here. Oh, good. 13 people are in the chat. All right. Okay. So what's the force of gravity equal to? So we'll call this one M1. All right, let's call this M1. And the reason I'm calling it M1 and not just M is because there's an M2 right here. Okay, and this is a common mistake that's made is when you go to calculate like the weight of something, you'll accidentally mix up one mass with another mass. Okay, and so to keep those separately, we'll just call one M1 and M2. Obviously, this one is M1G because it's the weight of the 13 kilogram box. What's that equal to? I'll try to do the math over here. All right, so we don't have to switch back. too much. M is 13 kilograms. Everything is an MKS unit, so we don't have to convert anything. And G is in is also in MKS units. It's 9.8, but we'll round it off to 10. And so that's going to equal 130 newtons, like that. Okay, there you go. There's the weight of the first box. All right. So continue, and the next one that you might look at is the normal force. Okay, and last time we did the normal force in red. Let's do it the same here, like that. And this is F normal. All right. And you don't have enough information quite yet to work out what that is. So let's just leave that alone for now. Okay. And then you ask, okay, is there another force? Well, when this system starts to move, it's going to start to accelerate this way. Okay. So it's going to start to accelerate that way. And then therefore the velocity is going to be in the same direction eventually. Again, it's going to accelerate down like that. All right, so this box accelerates to the right. This box here accelerates down. All right, and of course, if the box is accelerating to the right, the velocity will eventually be to the right, assuming it starts from rest, and that means that there's going to be a force of friction to the left. Okay, because the force of friction is in the opposite direction to the velocity. All right, and so if you look at what we did on Tuesday, even though that was on an inclined plane, we had these three forces. Okay, we had gravity, we had the normal force, and we had frictional force. But there's a fourth force here, and that's because there's a string pulling the box forward, and that's a tension like that. Okay, and so this fourth vector I will call Ft like that. All right. Now, we can do some analysis of the numbers here, but let's leave that off for a minute, okay? And let's look at the forces for the 6 kilogram box. We're done with the forces with the 13 kilogram box. There's just no other forces acting on that. Again, there's gravity down, there's a normal force up, there's a frictional force in the opposite direction to in which opposite to the direction in which the box is moving, and then there's a tension, okay, because there's a string which is actually pulling the box forward, okay, and you can think and you will realize that there's just no other forces acting on that. Okay, so what about the forces on the 6 kilograms? So this is a separate free body diagram, all right, and there are two forces. There's a force down like this, gravity, and this one is m2g, like that. All right, and that's going to be 6 kilograms multiplied by 10 newtons. 10 meters per second squared, and that gives you 60 newtons, like that, for the weight of the box. All right, and there's the force of gravity on it. Is there another force on that? Well, there's no normal force because it's dangling off at the end. It's not like this side is touching the table, like up here that was touching, but down here it's not. Okay, and there is no friction because again there's no touching, but there is the string there, and so there's a tension upwards like this. Okay, and that one is also Ft. All right, and just one more point before we start to put some numbers or see what numbers we can put on these things. There's a couple of subtle things here. Notice this acceleration here and that acceleration there. They're the same acceleration, okay? I didn't call one like A1 and the other one A2, all right? If I'd given them different names like 1A1 and A2, just like I did M1 and M2, then I'd be implying that A1 and A2 are different. But they're not. They're exactly the same, okay? And the reason the accelerations are the same is because the string doesn't stretch, okay? And neither does it bunch up. All right, so imagine that the 6 kilogram box drops by 1 centimeter. Well, then the 13 kilogram has to move to the right by 1 centimeter. If the 6 kilogram drops by 2 centimeters, then the 13 kilogram moves by 2 centimeters, and so on. Okay, and that means that the relative positions are the same, the relative velocities are the same, and also the accelerations are the same. Okay, and the other thing to notice is that this tension here and that tension there are the same. Okay, I didn't call this tension 1 and that one tension 2. Okay, and that one's a little bit more subtle. You might say, why are those two tensions the same? Like, why aren't they different? All right, and the reason is it's the third law. Okay, Newton's third law. All right, so just to remind you what Newton's third law says, it says, if one object exerts a force in one direction on another object, then that other object exerts a force back on the first object. Same magnitude, opposite direction. Okay, and so these two forces, Ft and Ft, have to have the same magnitude. All right, but you might notice they're not in opposite directions. And you go, well, does the third law really apply here? Because they're not in opposite directions. And the answer is yes, the third law does apply. Even in the pre-recorded lectures, I didn't do a full analysis, but you see there's this pulley there. And what the pulley does is it just basically changes the direction of Ft. If you did a proper analysis, which included, the two boxes and the pulley, then you would actually find that the third law, applies, including the direction. All right. So, that's a bit of a kludge, but that's okay. We'll skip those details and just realize that it is the third law, but then the direction is modified by that pulley. Nonetheless, that tension there and that tension there are identical. Okay, if you didn't make use of that factor, if you said that like one was Ft1 and the other one's Ft2, you wouldn't be able to solve the problem, and it'd be incorrect actually, because again, they are related to one another by Newton's third law. Okay, so that's how the diagram is constructed so far. And at this point, we can start to put in numbers. I know we already put in a number for the masses here. Okay, but we can see how far we can get with some of the other values here. So let's look at the normal force next. All right, actually, let me check if there are any questions in the chat here. I don't see any questions. Of course, just type in a question if you have any as I go along. And so we take a look at this normal force and just ask the question, is the box accelerating up or down? Like, is it accelerating down? Is it accelerating up like that? And the answer is no. There's no motion up or down, and therefore the normal force has to cancel the gravitational force. Okay, so this also has to equal 130 newtons. All right. Another way to think about this is suppose that the normal force is bigger than the gravitational force. If the normal force were bigger, then it would accelerate up off the table, and it doesn't do that. And if the gravitational force is bigger than the normal force, then it'd be digging into the table because it'd be accelerating into the table, and it doesn't do that. Because it's sliding, purely horizontally there's no vertical motion at all. There can be no component of the net force which is vertical, and so the normal force must exactly cancel the gravitational force. All right. The next one that we're going to do here is we can look at is the frictional force, and this time I can write out the symbol mu. Last time I didn't have my symbol mu ready. I didn't do it on the whiteboard, but mu. So FF, the force of friction, is equal to mu. That's the symbol for the coefficient of kinetic friction multiplied by the normal force. Okay. So this is why I go in the order that I do. I look at gravity first, okay, and then from gravity I was able to derive the value of the normal force, and then once I have the normal force, then I can derive the value of the frictional force. Okay, so it's good to go in that order. Gravity first, normal force next, frictional force next, and then any other forces you might have. Okay, and the reason it's this formula here, remember, is that friction is because of touching, but so is the normal force, and the frictional force is kind of like a fraction of the normal force. The harder these two surfaces push against one another, the more friction you're going to get. Okay, and that should make intuitive sense. Okay, because if that box is really pushing down on the table here, then it really kind of locks the box into the table and you get more friction. Okay, so if we substitute in the numbers here, this is what was it again? Let me look here. It's 0.25. Okay, so it was 0.25. In other words, 25% of the normal force. So the frictional force is 25% of the normal force, and what's that equal to? Let me just work that out very quickly. 130 multiplied by 0.25 is 32.5. So this is equal to 32.5, like that. And all right, good. All right, 32.5. And let me put newtons in there. All right. So if you look at what we have so far, we have the value of the weight, we have the value of the normal force, we have the value of the uh, frictional force, and the only other force remaining is the tension, and guess what? We don't know it. And you can't guess. There's just nothing that tells you what it is. The only thing you can say is that the normal force here has to be bigger than the frictional force. It has to be bigger than this 32 over here, okay? And the reason is that if Ft were less, then it wouldn't be accelerating to the right, it'd be accelerating to the left, okay? So whatever that Ft is, it has to be bigger than the 32.5, all right? But we don't know its value yet. Okay, so if we come over here to the 6, so we're done with the 13. If we come over here to the 6 kilogram, you know, we've got the weight of the thing, 60 newtons, and you say, do you know Ft? And you don't, okay? It's not equal to 60 newtons, all right? You might be tempted to say that, but if these two were equal to one another, then there would be no acceleration, okay? And so the only thing we can conclude is that Ft is less than 60 newtons. It has to be bigger than 32, and it's less than 60, okay? And the reason it has to be less than 60, because if it were bigger than 60, then this thing would accelerate up. Otherwise, or as it is, you know, if it's less than 60, then it'd be accelerating down. All right, so that's it for the diagram, okay? Spend a lot of time when you do these problems on the diagram. Think them through the way I did. And, you know, like you might have to go back and forth between like a page and like do some calculations. And then it's good to write the numbers in for the forces right into the diagram. All right. So we don't have Ft, but now we can use Newton's second law and come up with two equations and two unknowns to be able to solve for both Ft and A. Okay, I did ask for only A in that problem, but let's do that. So just remember before I switch to the other diagram or the other whiteboard that the normal force here, that's going to cancel the gravitational force. And the only thing that remains, the only two forces that remain are Ft and Ft is bigger than Ff. Okay, so let's switch to this other screen here. Okay, and over here, all right, we have that Ft, that's the tension force, we don't know how big it is, and we have that the force of friction was, I forgot already, 32.5 newtons, like that. And I'm not going to write the other two because they cancel out anyhow, okay? And by the way, this, I should probably say this one is for M1 equals 13 kilograms, okay? Because we're going to do this again for the other one. All right. So here are the two forces, and we don't know what Ft is, but we do know that it's bigger than Ff, okay? And so why did we do this analysis? Why do we always do this analysis where we identify all the forces? And the reason is because we want to get Fnet. Okay, so Fnet is kind of one of these key points in the problem that you want to get to in order to solve it, and that's because Fnet is equal to ma. What's that? That's Newton's second law. The only thing is that to not confuse things, this is actually m1 because we're talking about m1 here like that. All right, and you say, well, what's Fnet? Well, we argued that the gravitational force and the normal force, they cancel. So these are the only two things that go into Fnet, and Ft is the bigger one. Okay, so we could say that Ft minus the force of friction, which was 32.5, okay, that is your Fnet. Okay, so this Fnet, maybe I could just write it here, Fnet is equal to that. Okay, so that's what we get from the diagram. All right. Well, if we plug this into here, in other words, we have, like, we can't get a number for Fnet at this point. We just don't have enough information. Because we don't have Ft, we can't really solve and get a number for Fnet. But that's okay. Just when you're in those sorts of situations, you know, don't like FT isn't going to magically come to you. Just leave FT alone, leave it as a variable in your problem, and it'll work out in the end. Okay, so we're going to take your FT minus 32, that's your FNet, and we're going to say that that is equal to M1, which is 13, multiplied by A. Okay, and we'll call that equation number 1 because if you look at this, you can't go any further. All right. So this is usually a point where students get confused. If you're confused at this point, let me know here. But basically, just sort of like overall what we did is in the diagram, we looked at M1, we identified 4 forces on it, okay? And we went as far as we could in terms of giving each one a value, all right? And we decided that 2 of them cancel, so the only remaining ones were FT and FF, all right? And FNet then has to be the combination of FT and FNet. Okay, FT, maybe I could just say this. Yeah, it is bigger than FF, but the other thing is that it's to the right. Right, if you go back to the diagram, you'll see that that one was to the right. And the force of friction was to the left. So you can see that they're competing against one another. Okay, that's why they subtract. All right, so it's FT one way minus FF the other way. And that's going to equal your mass times your acceleration, which is Newton's law. All right, and there's 2 unknowns here, FT and A, and so that's it. You can't go any further. All right, so now what? All right, well, that's okay. We'll go on to M2. Actually, let's do it this way. Okay, there's M1, and here's M2, and M2 was 6 kilograms, like that. And let's switch back to the diagram. Whoa! Oh no! Oh yes, I know. I see it. Okay, you know what? Did it come back? There it goes. I don't know how long it was gone for you. So you know what? Let me just repeat a little bit of what I said. Yeah, like it's very strange. It'll go for a long time and it won't do that, and then sometimes it does that. Again, I promise I'll keep an eye on the one screen to make sure that it doesn't go blank on us again. Okay. So let me just quickly go over what I was saying here. I had for M1 equals 13. Wait, that's the wrong. That's very strange. That's the wrong one. Well, that's okay. It's actually it's my other screen, but it's still correct. But you know what? Let me switch to the proper one here. And okay, there we go. It's the same values. I just had the answer on the other one there. Okay, there we go. So let me just go very quickly over what I was saying there. M1 is equal to 13 kilograms. FT, we didn't know the tension. It's to the right. FF, that's the force of friction. We do know it's 32.5. It's to the left. The other 2 canceled out. Okay, and so the net force is going to be your FT to the right minus your force of friction to the left. All right, and so FT there minus 32. Sorry, 35, 32.5, not 30. Where are we here? 32.5. There we go. Okay, so FT minus 32.5. That's equal to MA. M in this case is M1 is 13 times A, and that's equation number 1. Okay, so now let me carefully switch to the other whiteboard, the diagram. So we're done with the Newton's law applied to M1. Let's look at M2 here. Okay, there are only 2 forces. Which one's bigger? The 60 Newton, because it's accelerating downwards. So the net force here is going to be the 60 Newtons minus Ft. Okay, so the 60 Newtons minus Ft. All right, let's switch back here. All right, and so over here we have that Ft is equal to unknown, and then mg was equal to 60 Newtons. Okay, and the net force in this case, F net, is going to be 60 minus Ft, which we don't know. All right, and so you don't know it, so just don't worry about it. Leave it as the symbol Ft. Okay, and when you get to this point that you've gotten as far as you can with F net, realize that F net is equal to MA, and this M is M2, so it's M2A like that. Okay, and what is that? Why can you say F net is equal to M2A? That's Newton's second law. All right, that's why F net is so important. As soon as you get F net, remember Newton's second law. And now for F net, we're going to put in 60 minus Ft. and that's going to equal m2, which is 6, times a here, which is just a. We don't know what its value is, and there's our equation number 2. Okay, let me see here. Good, we didn't lose the screen. All right. Okay, I'm going to switch back and forth very carefully here, and it's back. Yeah, Mateo, yes, it was, it's 32.5, not 32.2, okay? So thank you for pointing that out, all right? And so, well, at least you guys are following me, even though I did have a little bit of a technical difficulty there. And I lost it again, but we will recover it very quickly. Okay, there we go, all right? So now what? Well, at this point, the diagram isn't going to help anymore. It's just math, okay? Equations 1 and 2 are two equations and two unknowns. And so you have to just substitute one into the other. Luckily, it always turns out pretty easy, okay? And so what you could do is you could just put the two equations one on top of the other. So there's one equation, and here's the other equation, like that, okay? All right, so you got one equation on top and the other equation and the other on the bottom, okay? So what you do now is you just add the left-hand side to the left-hand side on one side, and that's going to equal the right-hand side plus the right-hand side on the other side, okay? And so over here, we'll just take this, and we will add it to this, all right? And on the other side, you're going to have that, and we will add it to that, okay? Like that, all right? So now, the reason this method works, it doesn't always work for two equations, two unknowns, but it works in these particular problems. So, like if you're in a math class and you try this trick, it probably won't work. But it works in this case because take a look here. See that FT there? That's positive, and it subtracts against that FT. So this FT, whoops, minus that FT, they cancel. All right, and then on the other side, you get 19, and so you're going to get here, let me just do the whole thing very quickly. So it's like 27 divided by 19. All right, it's equal to, so we get that, well, you know what, I better write down all the pieces here. So when you subtract the two, you're going to get 27.5, okay? And that's going to equal 19 times 8. And then when you divide, you get 1.44 meters per second squared, okay? And everything was in MKS units. So the answer turns out to be in MKS units, okay? Actually, it looks like it's more like 4 or 5. Not that that's a big deal, but it's 1.45, like that, okay? And there you go. There's the answer. Now, I didn't ask for the direction, but the direction is pretty obvious from the diagram, okay? The 6 kilogram has to be going down, and the 13 kilogram is going to the right, all right? So there you go. Now, the last thing, like if you're doing this on an assignment or a test, I always add a few because you've got five possible options to pick from. I always have some numbers in there which are just crazy. Okay, like you can never do this problem and get an answer over 10 meters per second squared. Why? Well, it can't possibly be that 6 kilogram. Let's go back to the diagram very quickly here. Like that 6 kilogram, it's falling, but it can't possibly be falling faster than 10 meters per second squared. That's like free fall. 10 meters per second squared is like free fall, and it's not free falling, it's dragging this other weight behind it. So whatever the acceleration you get, it has to be less than 10. All right, and so if you get an answer which is bigger than 10, or you see one of my answers like in the multiple choice, and it's like, I don't know, 25 meters per second squared, that's wrong. Okay, you just know that that's wrong. All right, and there you go. Okay, so 1.1 sounds about reasonable given the numbers that you have. All right, so let me look in the chat here if there's any other questions or comments in case something went wrong. Looks good. All right, let me switch back. All right, and I lost it, but that's okay. I noticed that I lost it, and we'll fix it very quickly. I've never really figured out why it does this sometimes and why it doesn't. I thought I did, but I didn't. Okay, so as long as I notice it fast enough, you won't be staring at a blank screen for very long. All right, so let's go on to part B here. Okay, So part B is a static friction problem. Okay, so I say repeat the entire problem, but this time the system doesn't move at all. Okay, and find the coefficient of static friction. All right, now I should say find the range of the coefficient of static friction, because when you do this, remember that the static friction has a minimum value. It could be bigger than that, but it can't be less than that without it slipping. Okay, but let's do this problem. And the technique when you have no motion is basically you start with the answer that you got. Like here, you notice that we have the acceleration was like our final answer. In this case, we start off with the acceleration is 0. And if the acceleration is 0, then you can conclude that F net is equal to 0 for both of the boxes. And that immediately puts a constraint on the forces. Okay? So let's do this problem. And you should, even though some of the numbers are going to be the same, you should probably rethink it from scratch, because it is a different problem. There's no acceleration. And as a result, some of the forces will change. Some won't, but some will. So you don't know which ones, so you have to rethink them. Okay, so let's go back to our diagram here. And let me just create a new fresh page like that. Okay, and let's start over. Here's our table. And here's the 13 kilogram box, like that. And here's the 6 kilogram box, like this. And here's the string around the pulley, like that. And there you go. That's what you would see, okay? And this is the 13, so I won't write anything there, and this is the 6, okay? So step number 1, draw what you would physically see in the lab, okay? Step number 2 is put in the forces and try to get values for them where you can, okay? So starting with the 13 kilogram box, there's gravity, straight down. There's no need to resolve it because it's on a flat plane, and we know how big it is. M1G is equal to 130 newtons, okay? So that one did not change at all. Okay, the next one was the normal force up like this. Okay, and since it's going to be canceling the gravitational force, it also is 130 newtons. Okay, for the same reason as last time, but it's even more so this time because it's not moving at all. It's not moving vertically and it's not moving horizontally. Okay, so there we go. Now there's a frictional force like this, and we'll call this one Fs, and we don't really know how big it is. Okay, we don't know. And the reason we don't know is because you can't use this formula here. You can't use mu k times Fn. Why not? Well, you see that k there? That's kinetic. Okay, so that formula doesn't work. You can't even use this. You can't even use mu s times Fn. Why? Oh, hold on here. There we go. You can't even use that. And the reason is that this Fs actually is part of an inequality. And so when it's an inequality, whoops, not 1. I don't know why I put a 1 there. But Fs is bigger than this. So you can even if you calculate this, it doesn't tell you what Fs is. It just tells you that Fs has to be bigger than that. And anyhow, you don't even know mu s because I didn't give it to you. Okay? So for all those reasons, you really just don't know what Fs is. That's okay. Let's leave it blank for now. And then there is the tension here like that. Okay? Ft. And you say, well, what is that equal to? We don't know. We do know one thing, though. All right? We'll use this in a minute. We know that Fs has to equal Ft in this case. It didn't before. Okay? Before, it was like, I don't know, we didn't calculate Ft, but we did argue that Ft had to be bigger because it was accelerating to the right. But this time, it's not accelerating to the right or to the left. Okay? And so that means these two forces have to cancel one another. Because if Ft were bigger, then it'd be accelerating to the right. If Fs were bigger, it'd be accelerating to the left. It's doing neither, and so they have to exactly cancel. Okay? All right, great. That's as far as we can go with the 13 kilogram box. All right, let me see if there's any questions. Oh, we're good. And I didn't lose the image. Great. All right, so it's when I know what one thing that triggers it, but why it's triggered sometimes and not another, I don't know. Okay, it's when I switch between two windows. But okay, so the 6 kilogram, what forces are acting on that? Okay, so always start with gravity. Gravity is acting down. This one is M2G, like that, and that's going to be 60 newtons. All right, down. Okay, and we have FT up, like this, like that. And now you go, do you know the value of Ft? And guess what? This time you do. You do know the value of Ft because these are the only two forces, right? That is canceling that one. Why? If the 60 Newton were bigger, it'd be going down. If Ft were bigger, it'd be going up. So Ft can be neither bigger nor smaller than 60 newtons. So guess what? Ft is equal to 60 newtons. In some ways, the static friction problem is easier. Okay, so up 60 newtons, down 60 newtons. What's A equal to? 0, because the forces cancel out. So Newton's first law says, look, if there's no net force, then A is going to equal 0. All right, and so that's the situation that you're in here. Okay, so this Ft, however, is equal to that Ft because of the third law. All right, and so guess what? This is equal to 60 newtons. And this one, that Ft has to equal Fs because we just argued why. It's not accelerating to the right or to the left, and so Fs is equal to 60 newtons. And so that, I think you would agree, is a lot easier because you've got all the forces, okay? And you never had to solve these two equations into unknowns, all right? Okay, so we've got all the forces for the 6 kilogram. We've got all the forces for the 13 kilogram. And now let me switch to the other board and just actually calculate it, okay? Let me see if there's any questions about this. All right, doesn't seem to be any questions. Great. Let me switch to the other screen here. Okay. And so, that F net is equal to 0. We made use of that already. When I was saying this is 60 newtons, therefore that has to be 60 newtons, we were doing that to make sure that F net was always 0. And the reason we always wanted F net to be 0 is because I tell you that A is 0. The system doesn't move, therefore A has to be 0. Okay, so at this point, we've got, we want to find the coefficient of static friction. And there is a formula for it, but it's not an equality, it's an inequality. Okay, so remember this from last time? It's going to be bigger than or equal to, all right? It's going to be bigger than or equal to, let me just move this up a bit, bigger than or equal to F static friction divided by Fn, like that. Whoops, F capital N, or I've been calling it little n, okay? So the static friction divided by the normal force, okay? So if we plug in the numbers here, and what was the static friction? Was 60 newtons, and the normal force was 130 newtons. And what does that work out to? 60 divided by 130, a little under a half. It's 0.46. There we go, like that. Okay, that's the coefficient of static friction. Well, not technically, that's the minimum value of the coefficient of static friction. Okay, so the coefficient of static friction is bigger than or equal to 0.46. All right. So it could be 1, it could be 2, it could be 20. As long as it's bigger than 0.46, the system won't slide. All right. If it were less than that, well, then we don't have a system that doesn't move. All right. So the coefficient has to be bigger than that 0.46. All right. Think of another way to think of this mu, either kinetic or static, is how sticky are the surfaces. The stickier the surfaces are, the bigger mu is. Okay. All right, great. That's it for question number 2. All right. So let me see here. All right, good. All right. Let's do question number 3, and then I think that's enough. All right. So that'll cover everything in your assignment. All right. So it says repeat 2A, and 2A was flat table, and things were moving, but this time the 13 kilogram is not on a flat table, it's on a plane inclined at 30 degrees. Now, the way I've written it there, it is a bit ambiguous, all right, because it's not clear which way it's inclined, that way or that way. So, like in the assignment, I say, and the 6 kilogram is trying to pull the 13 kilogram uphill, okay? I didn't write it here because I'm going to draw the picture in a minute, but when I do this on a test or an assignment, I'll make sure that the language is very clear, okay? And if need be, I can even create a diagram, all right? But I think the way I wrote it in the assignment, it was pretty clear because I said that the dangling weight was trying to pull the other one uphill, and that would only happen if you had um, uh, a particular configuration, which I'll show you right now. Okay, so let's create a new screen here like that, and change the zoom. All right, is that working? It is. Good. Okay, so like I guess you could have a table which is like that, but then the 6 kilogram wouldn't be trying to pull the 13 kilogram uphill. All right, so what I said is 13 kilogram gets pulled uphill like that. All right, well, I didn't write it, but I'm implying it. Okay, and here's the 6 kilogram like this, and this time the string goes around there like that, and there's the pulley like that. Okay, and what was the angle that I said? I said the angle was 30 degrees. So this angle in here is 30 degrees. All right. And obviously this is the 13 kilogram on this side right here. And this is the 6 kilogram there like that. Okay. All right. There's our configuration. Okay. So, and it is going to accelerate. All right. Because I said that it was. But here's the thing. With this problem, you're not sure which is going to win the tug of war. Okay, so let's think about this before we start drawing any forces on it. All right, one possibility is that the 6 kilogram wins the tug of war, and the system accelerates like that. Okay, but you might say, yeah, the 6 kilogram might win, but this is bigger. The 13 kilogram is bigger, although it's on an inclined plane. So I'm not sure which one's going to win. Maybe it'll go the other way. Maybe the 13 kilogram will win and it'll go that way. Okay. And the thing is that it doesn't matter which one you choose. As long as you're consistent throughout, you'll be okay. If you choose the wrong direction, then A will come out to be negative, and you'll know that you chose the wrong direction. Okay. All right. So what I'm going to suggest is that we choose this. This is going to accelerate that way. And of course, if that's that way, don't say that, because that makes no sense, because then that would be stretching the string. Okay, if this one's going down, then the 13 kilogram must be going up. All right, so I hope everyone's clear with that. All right, now I'm going to erase those in just a second. Okay, and the reason is because I got to put some force vectors in there, and it'll make a mess if I don't. Okay, so I'm going to just remove those, but just keep that in mind. All right, or maybe I could just write it over here. Yeah, let me do it over here. The 6 kilogram is just to remind us. Okay, and we know that the 13 kilogram has to go uphill. All right, so now what? Okay, so let's do the free body diagram for this one. So now, gravity straight down, but what do we want to do? We want to break it up into this way and that way. Okay, and this one is going to be m1g, and for these inclined planes, the perpendicular is cosine. Okay, so I'm not going to give the explanation right now, but if you go back to the pre-recorded lectures, I show you how I argued this. It's just a bunch of triangles. Okay, which is tedious, and so just memorize it. Memorize that this one's the cosine, and obviously if that one's the cosine, then this one must be the sine. Okay, so once you identify one of them, the other one is obviously the opposite. Okay, there you go. All right, so if you're good so far, let me just do this on my calculator. So m1 is 13, g is 10, cosine of 30 degrees. All right, so let me see what that gives me. That's going to be 130 multiplied by the cosine of 30 degrees. and that's going to equal 12.6. No, 112.6. All right. And the other one, sine of 30 degrees, that's one of those angles you should know it's a half. And so this one is going to equal 65 newtons. Okay. How do I know? Well, I mean, just it's one of those angles you memorize. If you do sine of 30 degrees, you'll find that it turns out to be a half. Okay. All right. Now what? So now the next force we usually look at is the normal force, right? And which way is the normal force? Typical error that's made, or I wouldn't say typical, but I've seen this error made, is, they'll just put the normal force straight up. Okay. Why is that wrong? Well, because the normal force, the word normal means perpendicular. Perpendicular to what? Perpendicular to the surface. Perpendicular to this surface right here, the touching surface. Okay. So perpendicular to that is this way, like that. All right. So there's your normal force. Okay. Good so far? And what other forces are there? Well, there's a frictional force and there's tension, just like there was before. The tension, let's do that one next because I think that one's kind of obvious. Tension's uphill like this, Ft. And the frictional force, which way is it? Well, let's think here. If this block is, whoops, I should be using red because if this block is moving down like that, accelerating down like that, then this block must be accelerating up like that, okay? And that means that the frictional force is opposite this direction here. And so let me rub those out. The frictional force is down this way, like that. Okay, and it's kinetic friction, and we've chosen a subscript little f to indicate kinetic friction like that. All right. We good so far? All right. So now, great. Now, like the order here isn't critical. You could look at like what the value of Fn is and then calculate the value of Ff and so on. Let's not do that right now. I'll do that on the other whiteboard. We've identified the forces, okay, for 13. We could, like I said, try to assign values to them, but so that I'm not switching back and forth all the time, let's just look at the 6 kilogram, okay? The 6 kilogram has a weight down like this, m2g, and we know what that is from the previous problem. It's 60 newtons. Okay? And there's a tension up like this. Whoops. Here. Okay, Ft like that. And we don't know how big either of those Ft's are, but the tension here is equal to the tension there for the same reason as before, okay, because of Newton's third law. All right. So is everyone good so far? All right. So take a look. This is about as complicated a problem as I'm going to give you. Let's look at the 13 kilogram. Okay. There are 4 forces. But gravity's broken up into 2 components: the perpendicular and the parallel. And so there's, in a sense, five pieces that we have to look at. Okay. So let me switch to the other screen here, and let's go through all 5 of those pieces. All right. So here we go, and over here, and let me make sure I didn't lose that screen. I did not. Good. Okay, and so we have the parallel gravity, m1g, and that was equal to, what was it equal to? The parallel was equal to 65 newtons. I don't know why I'm doing the parallel first. It doesn't matter. And then the perpendicular, m1g, was equal to, it was 112.6, 112.6 newtons, okay? So there's the 2 pieces of gravity. There was the normal force, okay, and we don't know the value yet. There was the force of friction, we don't know the value yet, and then there's the force of tension. We don't know the value yet. Okay, so there we go. Now, let's switch back to the diagram and take a look at if we can identify any of these. So usually I do normal force next. And take a look at that diagram. Notice that if you're looking at motion which is perpendicular, like that, okay, so motion which is perpendicular to the plane, there's only two forces that are involved, and that is the normal force and the perpendicular component of gravity. Okay, so those two are competing against one another. Which one wins? Neither. Because if Fn wins, then it starts to levitate off the table this way. If the perpendicular component wins, then it starts to dig into the table, so the two have to be equal to one another, and that tells you that Fn here has to equal 112.6 newtons. All right, so I'm going to write that in the other one, although you don't see me doing it right now, but all right, great. Now what? There's FF there, okay? And for FF, you say, well, can I calculate that? Yeah, this is kinetic friction, not static friction. And for kinetic friction, as soon as you have the normal force, and if you have mu k, you multiply the normal force times mu k and you get FF, okay? So for that one, actually, it's probably best if I switch to the other whiteboard like this, okay? And so over here, this is going to equal the coefficient of kinetic friction multiplied by Fn, like that, and that's going to equal 0. What did I say it was? Forget my own problems here. 25. 25%. 0.25. Okay. 0.25 multiplied by and let me do that on the calculator. 0.25 multiplied by 112.6, and it's equal to that, newtons. Okay, I guess we could round that off, but that's okay. All right, great. And now what's Ft equal to? Well, we don't know. Okay, so that's an unknown, like that. Okay, and don't lose sight of why we even did this. And again, we were doing this for M1. This is the 13 kilogram. Why do you do this entire analysis? Okay, so this is the point at which students kind of lose it because you get lost with all the details. You do that entire analysis just so you can get Fnet. Okay, so you say, all right, great. I've done that analysis. How do I get Fnet? Well, let's look at the diagram. For we're looking at the 13 kilogram. Fnet is the atom all up. Okay, well, we argued that this one cancels that one. Okay, so those two are out of the picture. There's only three that are left. It's going to be the tension, the force of friction, and the parallel component. There's three now that are in play. Okay, and which one has to be bigger? Well, if this is accelerating downhill like that, if the 6 kilogram is accelerating down, then this 13 kilogram has to be accelerating uphill. Okay, so if it's accelerating uphill, that means that Ft has to be bigger. All right, but what's trying to impede it? Both FF and the 65 newtons are trying to impede it. So the net force is going to be Ft minus the FF minus the 65 newtons. All right, so Ft has to be bigger than both of them. Again, why? Because if it weren't, then there's no way that Ft would be dragging it uphill. Okay, so Ft has to be bigger than both FF and the 65 newton. All right, so let's switch back to my other screen here like that. Fnet, which one's the one that wins? It's Ft. And what's competing with it? What's pulling it the other way? Well, FF is pulling the other way, and so is the 65 newtons. Okay, so Ft uphill. Actually, we can even say it here. Ft is uphill. Okay, the force of friction, that was downhill, and the parallel component of gravity is also downhill. Okay, so you can see here that the uphill comes in positive, the downhill is negative, and the downhill is negative, like that. All right, so we have FF I've actually got a number for that. And so I can write this as ft. We don't have ft, but we do have ff. And that's 28.15 minus 65. And what's that equal to? 65 minus. And I'm going to just round this off to 36.9. So if you're doing it, you will have an extra decimal, but that's good enough. We should only keep 3 significant figures anyhow. Okay. So whoops, ft minus that. All right. So is everyone good with what I did there? We don't know ft, so I can't put anything in for that. We do know ff. That's 28.15. We do know the parallel component. That's 65. Both the force of friction and gravity are trying to pull it downhill. That's why they come in negative. Ft is the only thing that's trying to pull it uphill. So it's Ft minus against the other two. Okay. And I did that wrong because there's no way that 65 minus. Okay, hold on here. What did I do? I changed the minus into a plus. And so it's 93.2. Yeah. All right. Sorry about that. Okay. Everyone see how I did that? Looking in the chat here. All right. Looks good. Okay. So now, once you get FNet, set that equal to MA. All right. Because FNet equals MA. It's M1A in this case. All right. And so for FNet, we don't have a number, but at least we've got that much. Okay, we've got something. All right. And then for M1, we have 13 times A like that. Okay. And that's it. That's as far as we can go at this point for the 13 kilogram. Okay. Let's look at the 6 kilogram next and switch back to the diagram because you might have forgotten. All right, so it's accelerating downhill. There's that 8 off to the right there. And it's accelerating downhill. That means the 60 must be beating the FT. So 60 minus FT, that's your FNet. All right. So it's easier for this one because, there's only 2 forces and they're exactly opposite one another. Unlike the other one, which had, like 5 forces in different directions. But even though they're like 5 forces and 5 components of forces, there's still, you're always trying to make that characteristic T, because that characteristic T is what allows you to add up these forces as vectors easily. Okay. So back to this one, 60 down minus FT up. That's got to equal your MA. All right. So over here, we have that F. Oh, something happened. There we go. FNet is equal to M2A. All right. FNet in this case is, we said 60 down minus the FT up. All right. So if we substitute that into this one here, actually, let me just write it over here. Okay. So for the FNet, we're going to put in 60 minus FT. That's going to equal, for the M2 here, we're going to put in 6 times A. And again, one equation, but 2 unknowns. You can't go anywhere with that. And so we're in the same sort of situation as we were before. We've got these 2 equations. And so it always works out that if you add them, the FTs will cancel out. Okay, so if we add these, we'll get FT minus 32 plus 60 minus FT. That's going to equal 13 plus 6 is 19A, like that. And notice that you have a positive FT and a negative FT. So the positive FT here cancels that negative FT there. And what do you discover? You discover something kind of interesting, that when you add these together, you're actually going to get negative 33.2 is equal to 19A. And then A is going to equal, let me calculate that for you. divided by 19 is 1.74 negative meters per second squared. All right, negative. What happened? Why did we get a negative in there? Well, because I purposely chose the wrong direction. I wanted to show you what happens if you choose the wrong direction for A. Okay, it's not a disaster. What happens is basically you made the wrong assumption for A, and so you got a negative value. So if we go back to the diagram here like that, we assumed A was that the 6 kilogram block was going to be enough to pull the 13 uphill. It isn't. It's not going to be enough. Okay, so actually the way this would go is, this is wrong. This one would accelerate uphill like that, and this one would accelerate downhill like that. But we do know what the value is. It's like 1.74 meters per second squared. Okay, does it make sense? Yeah, again, that number 1.74, it's like it's not bigger than G. Okay, if it were bigger than 10, then you did something wrong. Does the direction make sense? It's kind of hard sometimes to intuitively see which direction would win, but I don't know. I mean, like, yeah, sometimes it's obvious, sometimes it isn't. To be honest, I think if you had guessed ahead of time, good for you. But to be honest, if you didn't see which way it was going to go, don't worry about it. You just make sure that you choose one direction for A. You're consistent all the way through, and then you're done. Okay. So all right, we're done with that problem. And now what we're going to do is we're going to repeat this, but assuming static friction, and it's going to be a lot easier, as you'll see. Okay, so this time I say repeat 2B, but the 13 kilogram box, I don't know why box is, there we go, on an inclined plane. So just 2B was like you have the system doesn't move. Okay, so basically we've got exactly the same diagram as this, but there's no acceleration. Okay, and this diagram is messy, and you should start from scratch anyhow, because you might mistakenly use a number from here that is not relevant for the other problem. So let's start over, and this shouldn't take too long. So let's create a new whiteboard like that. Let's draw the inclined plane like this, and this angle down here is 30 degrees. And there's a box here like this. There's a box here like that. This comes around here like that. There is a pulley here like this. Okay. And that's it for the first step. Okay. Now what? Next thing is get your identify all your forces. So let's start with the 13 kilogram box. Gravity, 2 pieces, the perpendicular and the parallel component. Now, if you think about this one is mg cosine theta, and the other one's mg sine theta, okay? But the numbers are going to be the same, aren't they? Because m is the same, g is the same, and theta is the same, okay? And so you could just write in the number here. And actually, I forgot what it was. What was it? The perpendicular component was 112.6, so this one was 112.6 newtons, like that. And this one was 65 newtons, okay? There you go. So I didn't really skip a step, I just went very quickly. I know that mg cosine theta is going to give me the exact same number of 112.6, and the other one, mg sine theta, is going to give me 65. All right. And then what other forces are there? Well, there's the normal force this way. And sorry, that it's supposed to be perpendicular. There we go. Okay. A little bit better. All right. All right. And there's a tension uphill like this. And there's a force of static friction. We'll do that one in green. And can you guess which direction it's going to be in? Well, you might not have been able to guess if we hadn't done the previous problem, but you now know that in this tug of war between the 13 and the 6, it's the 13 kilogram that would want to win and pull this downhill like that. And so the frictional force is going to be what? In that direction there like that. Okay, and this is F subscript S. Okay, does everyone, whoop, I made a mess here, hold on. There we go. Let me do that again. F subscript S like that. Okay, so does everyone get why the direction for FS? It's uphill because, think about it, like if I know that there are different problems because one is moving and the other one's not moving, but if it were to move, which way would it want to move? Well, the 13 kilogram would want to win. Okay, it'd want to win, and that means that it'd want to pull that downhill. Okay, and so so there it is. Okay, and then over here we have this one, which is 60 newtons, and then uphill here we have FT like that. All right, but we know that these two are equal to one another. Okay, and so because it's not accelerating, this one's 60 newtons. All right, and we know that this one must equal that one, so this one is 60 newtons like that, and we know that this one must cancel that one because there's no motion in the other direction, so this is a 112 newtons, 112.6 newtons. Okay, and we're almost done. We don't know FS. Okay, we don't know FS, but without even having to go to the other board, can you guess what FS has to be? Well, let's look at this. We've got 65 pulling downhill and only 60 pulling uphill. Who's winning? The 65 is winning, right? So that would want to pull this downhill. So you know what that means for this one right here? How big does that one have to be to make them balance out? Well, it's got to equal 5, doesn't it? It's got to equal 5 newtons, because then you'd have 60 plus 5 uphill balancing the 65 downhill. Okay, so I hope I didn't go too fast with that, but I mean, in problems where you have no acceleration, it's usually a lot easier because you know from Newton's first law that everything has to add up to 0. And if everything has to add up to 0, that means that the two forces up the plane have to cancel the force down the plane. Down the plane we have 65. So the total up the plane has to be 65. We've only got a tension of 60, which means that the static friction has to be 5 newtons. Okay, so I guess I could do a little bit of that on the whiteboard, but I think it's pretty clear, and we lost it. That's okay. We'll fix this. There it is. Okay. So over here we have that. We have that what? We have that F net. This is for the 13 kilogram. M1 is equal to 13 kilograms like that. Okay. F net has to equal 0. Why? Well, because there's no acceleration. I guess I should have said that maybe first. A is got to equal 0, right? Why? Because we're static friction. Okay, so there's no acceleration. Now what? Well, that means that F net has to equal 0. Okay, so what does that mean? That means that, let's go back to the diagram very quickly. The force downhill, that's a 65 Newton. All right, so let's take downhill as positive. So F net is going to equal 65. All right, downhill. You didn't see me typing that, but I'll show it to you in a second. That's got to balance again the 60 uphill, negative, and the FS uphill, negative. Okay, so minus 60 minus FS. Okay, so let me switch back. What did I write? So the acceleration is 0. That means the net force is 0. But the net force was 65 newtons downhill minus 60 newtons because that was uphill minus the Fs, which is also uphill. And what's that got to equal? That has to equal 0 because there's no acceleration. And I think it's pretty obvious that means that the force of static friction is 5 newtons, like that. Okay, so now what? Well, I technically want the coefficient of static friction. So if you take a look up here, the coefficient of static friction is given by this formula there, like that. All right, coefficient of static friction. Static friction here is 5 newtons. And the normal force, what was it again? I'm looking at the diagram. So 112.6. 112.6 newtons, like that. And that's got to equal 5 divided by 112.6. And that turns out to be a really small number, but there it is, okay? So as long as you're bigger than 0.044 for your coefficient, it's not going to move, okay? So yeah, it's a small number, but that's okay. It's the smallest it can be, okay? If it's smaller than that, like if it were like 0.03, well then it would slip, okay? But if it's 0.044 and above, then it's fine. All right. So that's it for the class. I hope that helps. And I don't know, I'll wait just a few minutes to see if you have any questions. I'm also going to entertain any questions that you might have about the assignment. If you don't have any questions about the assignment because you haven't tried it yet, I'm on my Google Hangout in the evenings, and I'll be happy to help you, okay? If you wait till Friday evening, hopefully you won't do that, but if you do, and everyone tries to catch me on in a Google Hangout at the same time, it has a limit of 10, and also even at 10, it gets pretty hard to answer everyone's questions. So really try to get at that assignment and try everything today, okay? So let me take a look here in the chat if there's any questions. Oh, it doesn't seem like there are any questions. So let me just say here, any questions? All right. Okay. We'll see you then. Bye-bye.